balance is to be recovered by compressing the displaced gas to a total pressure of 5 atm and then cooling it isobarically to a temperature of to a certain temperature. We're trying to determine what that temperature is. So this is kind of using Raoult's and Antoine's in reverse. So first we're going to use Raoult's to figure out what the vapor pressure is. Instead of usually we're solving for the mole fraction, now we're going to solve for the vapor pressure. And then we're going to use that vapor pressure and the Antoine's constants to solve for the temperature. So just doing kind of like the reverse of what we just did to back calculate the temperature. So first, let's draw out our system. And we have this inlet stream, which is this gas. And because we are just dealing with mole fractions and temperature and pressure, it doesn't matter how many like moles that we're feeding into the system, so we can just assume just an arbitrary basis since it doesn't really matter when it comes to solving our problem. It's not going to change our answer, so we're just going to assume 1 mole enters. And we know the composition of this gas here because we figure out that it's 0.0469 is the mole fraction of toluene, and then the rest of it, which is 0.9531, is just gas. We don't know what the gas is. And then, so we have some of it remains as vapor. So we have some number of moles of vapor coming out. And we're trying to figure out what that temperature is, and we know that that is at 5 atm. And we have some mole fraction of toluene in the vapor, and then some mole fraction of gas. And then here we have some number of moles of toluene leaving. And we know that this number of moles of toluene leaving is 90% of the toluene in the feed, since we're compressing 90% of the toluene. So the first piece of information that we're going to use is the 90% of toluene condensing. So NL, which is the liquid toluene, is going to be equal to 90 or 0.9 times the 1 mole of feed entering times 0.0469, which is the mole fraction of toluene. So 0.9 times 1 times 0.0469 means that we have 0.04221 moles of toluene, and that is NL. So that's how much is condensing. Now we can do a total mass balance, and we know that 1 is equal to NV plus NL, and we just solved for NL, so NV is going to be equal to 1 minus 0.04221, so NV is equal to 0.9578 moles. So now we can do a toluene balance, and we can figure out the mole fraction of toluene in this gas. So we have 0.0469 times 1 mole entering is going to be equal to NV, which is 0.9578, times Y, plus 0.04221 moles of toluene. So then minus 0.04221 0.4221 over 0.9578. We end up getting that y is equal to 0.0049. So that is the mole fraction of toluene in the gas. So now we can use Raoult's law to determine the vapor pressure of toluene. So the vapor pressure is going to be equal to the mole fraction of toluene in the gas times the pressure of the system. So that's 0.0049, which is the mole fraction, times the pressure in the system, which is 5 atm. And we need to convert this to millimeters of mercury. So there's 760 millimeters of mercury in 1 atm. So 0.0049 times 5 times 760. So that is 18.62 millimeters of mercury. And that is the vapor pressure of toluene. So now we're going to figure out the temperature that corresponds to this vapor pressure using Antoine's. So if you rearrange Antoine's to solve for temperature, you end up getting that B temperature is equal to B minus C times A minus log 10 vapor pressure over A minus log 10 vapor pressure. So when we plug this in, so we have 1346.773 minus 219.693 times 6.95805 minus log 10 of 18.62 over 6.95805 minus log 10 of the vapor pressure, which is 18.62. Oh, that was quite the mouthful. 0.773 minus 219.693. And we end up getting that the temperature is equal to 17.08 degrees Celsius, which is about 62.7 degrees Fahrenheit.